combined gas law. You heard Boyle's law. You read about Charles' law, Gay-Lussac's law, and you just said, I can't get enough of these laws. I just love gases. All types of gases. So, let's read. Combined gas law reading. The three gas laws studied so far, Boyle's law, Charles' law, Gay-Lussac's law. Let's see, hold on. Let's see, this is pressure and volume. Charles is volume and temperature? Is that right? Gay-Lussac's is pressure and temperature, I think. I might have these switched. Oh, you should probably go check. Can all be combined into one equation, that's nice, called the combined gas law. Using the combined gas law simplifies the life of a chemist. Well, makes sense, because there's only one equation. Because whenever the chemist needs to recall the three specific laws, they can just cancel out the variable that is constant as shown to the right. To the right? What? Variable that is constant is what you cancel out. That sounds really important. This is actually below. Looks like it moved. Also, the combined gas law allows chemists to calculate gas changes even when all three variables change at once. That's new. Keep in mind the temperature must always be in Kelvin, so the temperature shares the same zero with pressure and volume. Remember, this is absolute scale. Shares the same zero. Let's look at those graphs. I flip back to page 17. Boom! There they are. Charles' law, volume and temperature. Ooh, is that what I said? It was! So I was right. Okay, and so, yeah, they're going up. It's proportional. Oh, but look, it says it's proportional only to the Kelvin temperature. And I guess they've got the same zero, because this is 0 volume, 0 temperature. But I guess it wouldn't work if it's Celsius. And then here, the same thing. They've got the same 0. So it's got to be Kelvin. Otherwise, I guess they won't be proportional to each other. So no Celsius, only Kelvin. Oh, here's the figure that they said to the right. So let's see. So this is a combined gas law. P1V1 over T1 equals P2V2 over T2. And then we've got constant temperature. So that would be Boyle's law. This is constant temperature. It's Boyle's law. And then constant pressure. That's Charles' law. Constant volume. That's Gay-Lussac's law. I don't know why I just highlighted things. I wonder if you even have those colors. Okay. So I guess this makes sense, because think about it. If you have constant temperature, that means T1 equals T2, and they would just cancel out. Like, you could plug them in, but they would just cancel out anyway. But that's only for Boyle's law. Like, if it were Gay-Lussac's law, constant volume, then this would cancel out, and you'd be left with P1 over T1, P2 over T2. But we don't want to actually cross those out. Ooh, math. Okay, so let's see what's going on here. A balloon contains air at about room temperature. It's cooled from 300K to 150K using liquid nitrogen. Oh man, if you know anyone who has liquid nitrogen, let me know. If it ends up being, like seriously, if it ends up being 7.5 liters, what was the original volume, assuming that pressure's constant? Okay, pressure's constant. So if we go back, that would be Charles' law, constant pressure. So we're going to use this one. Okay, it looks like they identified all their variables. We're looking for V1. Look at that. They're canceling out P. Yep. They're plugging it in. Yep. So let's see. We cancel. We should annotate, right? Cancel P. Plug in. Now what are they doing? Looks like they're multiplying by 300. So we multiply, because they're trying to get V1 by itself, I guess, by 300K on both sides to isolate. Do your math teachers use that word? That's what my math teachers always said. And then that cancels out. The K's cancel. 300 over 150, that's 2 times 7.5 is 15. So the original volume was 15 liters before being cooled. You probably could have figured that out just by looking. I mean, the temperature gets in half. So that means the volume must have been cut in half if the pressure stays the same. So then, if we just go backwards, we double the volume. But still, it's good to be able to plug it in. Let's look at this next example. If a sample of gas has a temperature of 27 Celsius, got to convert that to Kelvin, add 273. Remember, it's only Kelvin that is proportional to a pressure of 4 atm and a volume of 10 milliliters, so milliliters, after a process, and had a pressure and volume of 6 atm and 20 milliliters before the process. What was the initial temperature? So that's T1. Okay, so they collect everything. We're looking for initial temperature. We circle what we're given here. I think I forgot to do that on the other one. I just got too carried away. Okay, they get that. We're looking for T1. So I guess we don't cancel out anything here because everything is changing. We plug it all in. Now we got T1, but got to get it by itself. Problem is it's on the bottom, right? So to get that off, you would multiply T1 to both sides. Oh wait. Okay. They just got rid of the fractions completely. Oh, I see. I see what they did. They cross-multiplied. So here we cross-multiplied. I wonder when you know to do that. Because we didn't do it for the other one, but it had fractions, right? It had fractions, but we just multiplied by 300. We didn't have to cross-multiply. But here you have to cross-multiply, I guess. So they did that, right? Cross. They get that. Now we got to get T1 by itself. So how do we do that? We divide by everything else. 4 atm, 10 milliliters, that's gone. And then we got that. The units cancel. We can simplify. 20 divided by 10 is 2. We can cancel out a 2 here. 3, 2. And then this becomes 150. I guess I could have canceled those 2's, huh? That would have been faster. Then we get 2 times 150 is 300, times 3 is 900. So the initial temperature must have been 900. Well, I hope you enjoyed our amazing video here. I hope it was a hoot. And come back for some more later. Bye-bye now.